Imagine waking up in the spring and discovering your dock has moved, not inches, feet, pilings bent, frames twisted, deckboards broken, and all of it happened while nobody was there. The culprit? Ice. Every winter, expanding lake ice causes millions of dollars in dock damage across North America. But contrary to popular belief, it's often not the weight of the ice that destroys a dock. It's the tremendous horizontal and vertical forces created as ice expands, contracts, and bonds to structural components. In this video, we'll explain the engineering behind ice heave, analyze the most common dock failures, and show you how to design a dock that has a much better chance of surviving harsh winters. Let's get started. What is ice heave? Water is a polar material. It has a positive and a negative side, which causes it to behave differently than almost every other liquid. As it freezes, it expands by about 9% in volume. Now imagine an entire lake freezing. That expanding ice sheet behaves like a massive moving plate. When temperatures fluctuate, ice expands, ice contracts, ice cracks, ice refreezes. Wind pushes enormous sheets. All of these forces can act on docks. Most dock owners think only about vertical lifting, but docks experience several different kinds of loads during winter: vertical uplift, horizontal pressure, ice adhesive, wind-driven ice sheets, thermal expansion. Each force attacks the structure differently. Expansion force on this diagram is the blue arrow showing that as ice forms and thickens, it expands outward in all directions. The red arrows show the horizontal pressure. The expanding ice pushes horizontally against the dock and pilings, causing lateral stress and potential movement. The yellow arrows show the vertical uplift of the dock with its pilings. The expanding ice lifts upward, exerting vertical forces on the dock and pilings. The green arrows show the wind movement across the ice surface, causing drift and additional pressure on the dock. So why do docks fail? Most failures don't happen instantly. Damage accumulates over years. Typical failures include bent piles, broken welds, cracked concrete, split wood, loose connections, twisted frames, lifted footings. Once one connection weakens, the entire frame begins redistributing loads, and that often leads to progressive failure. Pilings resist enormous loads, but ice changes everything. If ice bonds tightly to the piling and the water level changes, the ice can attempt to lift the piling. Meanwhile, expanding ice pushes sideways. Those combined forces create bending moments. Eventually, steel bends, wood cracks, concrete fractures, connections loosen. The red arrows in this diagram show the horizontal pressure. Wind and currents push against the ice sheet, transferring horizontal load force to the piling. The yellow arrows show the upward lift force. As ice forms and thickens, it expands upward, lifting on the dock and the piling. Floating docks move with changing water levels. That flexibility often reduces stresses from changing lake levels, though they can still be affected by moving ice if left in place during winter. As water levels rise or ice expands, the dock rises and moves, reducing stress and damage. Permanent or fixed docks resist movement. They are fixed to the lake bottom. Ice expansion and water lift create high stress on the structure and pilings. That strength is excellent during summer, but during severe winters, rigidity becomes a disadvantage if ice loads exceed the design. Different lakes require different solutions. Fortunately, many failures are preventable. Good design starts with understanding local winter conditions. Common strategies include removing seasonal docks before freeze-up, using floating docks designed for seasonal removal, installing properly embedded piles, adding cross bracing, selecting corrosion-resistant hardware, allowing for thermal movement where appropriate, using ice management systems in locations where they're practical and effective, such as an ice bubbler or a de-icer. The best solution depends on climate, lake conditions, and dock type. Winter ice damage risk by dock type. This comparison shows which dock types are generally more exposed to the ice damage during winter. On the left side is low risk, seasonally removed floating dock. A dock that is removed before the lake freezes has very little exposure to ice pressure, ice movement, or freeze and thaw cycles. Next to it is a moderate risk floating dock left in water. A floating dock can move with changing water levels, but shifting ice may crash flotation units, damage hinges, or push the dock toward shore. Moderate high risk is the pipe dock. Pipe docks have narrow supports which may reduce some ice contact. However, ice can still bend the pipes, lift the legs, or twist the frame. High risk is the timber pile dock. Ice can freeze tightly around timber pilings. When the ice rises, falls, or moves sideways, it may lift, lean, or crack the pilings. Another high risk is the steel pile dock. Steel pilings are strong, but a rigid dock may absorb significant horizontal ice pressure. Welds, braces, and connections can fail even when the pilings remain intact. And the highest risk is a large, rigid, fixed dock. A large permanent dock presents more surface area for the ice to push against. Because it cannot move easily, ice forces may bend pilings, twist the frame, or lift sections of the structure. In general, the safest dock during winter is one that has been removed from the water before freeze-up. Docks left in place face increasing risk as they become larger, more rigid, and more exposed to moving ice. However, dock type alone does not determine whether a structure will fail. Water depth, ice thickness, wind direction, changing water levels, pile depth, bracing, connection strength, and local shoreline conditions all affect performance. This comparison is intended to explain the general risk. It is not a structural rating for every dock. After winter, the warning signs. Inspect your dock every spring. Look for uneven decking, leaning piles, new cracks, loose fasteners, separated joints, warped frames, rust, broken welds. Early repairs are usually far less expensive than waiting for a major failure. Ice is one of the most powerful forces a dock will ever experience. Understanding how ice expands, bonds to structures, and transfers loads can help you make better design decisions before winter arrives. Whether you're building a new dock or maintaining an existing one, proper engineering, routine inspections, and choosing a design suited to your local climate can dramatically reduce the risk of costly repairs. If you found this analysis helpful, please like the video, subscribe for more dock engineering and waterfront construction content, and share your experiences with winter dock damage in the comments.